Hello, it's Keith here, and this is lesson 13 of the platform-specific series of my Z80 programming tutorials. Now, today we're going to be having a look at the Amstrad CPC and the Amstrad CPC Plus, and we're going to learn how to do palettes on those systems. Now, in the past we've looked at how to get graphics onto the screen, but we haven't looked at how to actually select what colour those graphics will appear from the system's palettes. And so today we're going to do that, and we're going to do it twice. Once on the Amstrad CPC, the regular Amstrad CPC, and one on the more advanced CPC Plus. So we're going to do things in a slightly unusual way when it comes to doing palettes. So we're going to use the CPC Plus's palette definitions, which use a single nibble for green, red and blue with one nibble unused. So that's a 2-byte palette definition. And we're going to use that palette definition on all of the systems we're going to look at, even if the system that we're looking at has more or less colour options available to it. So today we're actually going to use these CPC Plus style palette definitions to define our palette on the Amstrad CPC, which just has a 27 colour palette. So you might think that's quite wasteful from the point of view of selecting the colours on the CPC, and you're correct, of course it is. But what it does allow us to do is it allows us to save a lot of time when it comes to programming one game onto a lot of different systems. And with Grime Z80 I was able to use the same palette definitions on almost all of the systems that I was working on, with the exception of things like the MSX1, which has a very specific palette, and that needs to be set per line of the sprites. So with that system it wasn't appropriate. But with the new game I'm working on, the my Chibi Academy's mini game, I'm actually using even these colour definitions to define the colours on the ZX Spectrum, because it's easier for me to write code that once and then convert that code in real time onto the hardware of the system than it is for me to write palette definitions for 4 different systems or more in the case of Grime Z80 and test them over and over again. So we're going to have a look today at how to use this colour definition code on the CPC Plus, and then how to convert it into a very simple palette for the CPC with its more limited palettes. This is also going to be the first time we look at the CPC Plus, so we're going to discuss how to actually turn on the enhanced features of the CPC Plus, because there's a few little tricks we have to do first. So you can see in this window here, this is the example we're doing. It's basically the same bitmap example we looked at before, but now we've got the colours defined using this new code. So this is the basic CPC version. If I just open my code window here, and if I just unrem this option here, so now we've built the CPC Plus version. And here you can see the CPC Plus version. Now the background's slightly grey there, and the reason I've done that, it's intentional. What I've done is I've selected a palette definition that's very dark, and so on the Amstrad CPC there is no equivalent, so it ends up being converted to the next lowest option, which is black. But on the CPC Plus with its 4096 colour palette, it's able to do that dark grey quite nicely. That's, as I just said, the CPC is capable of 4096 colours. It's not the best to the MSX. The V9K can do more colours, but a lot of systems can do less. So I've decided to use the CPC Plus definitions across all of the systems and convert as needed, because, to be honest, 4096 is enough to do smooth fades. Chibi Academy's did fade in and fade out and fade between colours, and it's perfectly enough to do that, but it's not ridiculously more. It seemed excessive to use 256 colours per channel and use 3 bytes per colour definition, because really none of these systems really can support that kind of colour depth. Even things like the Game Gear doesn't have that kind of colour depth, so it seemed excessive doing that. So let's just have a very quick look at the code example we're doing today. We're not going to discuss the drawing the bitmap because it's exactly the same as it was before. So we've got this new palette routine. We load in our palette, we select the number of colours because we're doing a loop. Now if we try and set colour 16 with our palette command here, it will actually set the border of the system. We're only supporting up to 16 colours, so 0 to 15. 16 will set the border on all of our systems we're going to look at in the future, if that's applicable. So we're loading in here we're loading into DE, but then we're swapping to HL. So when we call set palette, we've got a number from 0 to 15 or 16 for the border, and we've got HL, which is the byte color definition, and you can see our color definitions here. So this is that dark grey, this is bright white, and you can see this is purple and this is cyan. So here's the color definitions here. So let's actually have a look at the CPC code then that's doing this work. So let's start with the CPC Plus, because as I said, this definition is basically a CPC Plus definition. Now the first thing we need to do is we need to tell the CPC Plus that we want access to the advanced features of the CPC. Now this is a little bit odd. What we do is we send this strange sequence of bytes to the gate array. The gate array is one of the chips in the CPC that deals with some of the graphics system and also with regards to the memory mapping. We send this weird set of bytes to the system. This will have no effect on a basic Amstrad CPC, so you don't do any harm if you do this. But on an Amstrad CPC Plus, it enables the advanced features. Now these bytes have no meaning at all. Essentially, when the Amstrad CPC Plus was released, they claimed that the CPC Plus features could only be used on cartridge-based games, so that the tape and disc games would never have the advanced features and you'd have to buy the more expensive cartridges. It wasn't quite true, because this sequence of codes could be sent via any game, and that's how we're doing it. But the companies that agreed to manufacture cartridges had to sign a non-disclosure agreement confirming that they wouldn't release the information to do this, so it was more of a legal restriction stopping people from doing it in the disc and tape games than actually a physical one. There is no physical limitation at all. When it became clear the CPC Plus was a failed system, they gave in and said, well, okay, it doesn't really matter anymore. And so you started to get the games that came out on disc, and of course the free stuff coming out now that use this feature. So don't try and work out what all these codes mean. They don't mean anything at all. Now, once we've sent these commands, we do have some quite important commands. We have a command where we send out 7FB8, and we have a command where we send 7FAO. Now 7FB8 will turn on what's known as the plus registers. This is a special memory bank that appears in the normal memory bank between 4000 and 7FFF. So when we page it in, this memory bank appears. When we page it out, this memory bank disappears. And this means we won't be able to use that memory while we're doing good stuff with the plus registers. And this makes it especially important where, if you remember, the Amstrad CPC has a special option where you can bank in a single bank 7, to the top of the memory outside of this range on the 128K systems. And this makes that bank very important, because if we want to have extra sprites, really we have to have them in our standard memory, which of course will be very limited already, or in that 7th bank, because that's the only bank we can put in that high position. Another very important thing I will tell you now, because this caught me out: if you're using an unofficial memory upgrade, which I do because my CPC 128K has a broken internal memory bank, so I use an external XMEM memory upgrade to bypass the internal memory. But while the internal memory will work fine no matter what you do, the external memory, if you've got one of the 128K memory banks paged into this range, and then you page in the plus memory, it will not work correctly on some external memory systems. So what you need to do first is either make sure you've got that 7th bank paged into the top of the system memory, or you turn off the 128K banks and just have your memory set to the default 64K before you run this command. Now, in my example here, we're not using 128K memory at all, so we don't need to worry about it. But if you're writing your own game, 128K games, before you start doing things with the plus memory, turn off your 128K banking back to your default internal 64K before paging in the memory, or you might get malfunctions. And the trouble with that is you won't get malfunctions on your emulator. You may not even get malfunctions on your computer. It will be the person who's got a 464 Plus with a memory upgrade who will start complaining you're saying your game doesn't work on my system. So please bear that in mind. But, you know, if you're just starting out, if you're just a beginner at this, and if you're just playing around with emulators, of course, this is nothing to worry about at this stage. I just wanted to warn you of a major problem that, I probably spent a day or something scratching my head and running between my computer and my CPC with SD cards, trying to work out what the bug was and trying to fix it, because I couldn't replicate the problem on the emulators. So please bear it in mind. Now, once we've paged in this special so-called ASIC memory between 4000 and 7FFF, we will get various memory in that range that does different things. Part of it is, of course, the sprites. Part of it is other things like the interrupt management, because the CPC Plus has better interrupts, which we will look at later. But all we're going to look at today is the color information. So each color definition is 2 bytes in the format we just discussed. So unused byte, green, red, blue, as you can see here. The first color definition is a hexadecimal 6400 in that ASIC memory, and they proceed to 641F. The next color information is for the border, and then there's a further 15 colors for the sprites, because the hardware sprites use different colors to the system colors. So you can kind of get 31 colors on screen. I say 31 because color 0 on the sprites is transparent. So how do we actually set the palette? Well, it's very easy. First we page in the ASIC memory here, and then the between 4000 and 7 FFF will be this special memory for configuring the CPC Plus options, and we use it just like our normal memory because to the Amstrad it is our normal memory. So when we call this function, we will have A set to the color number we want to change, so 0 to 16, and we'll have HL set to the new value for that color. We swap DE and HL, so the color information is now in DE. We load the start of the palettes, which is 6400. Now, each color definition uses 2 bytes, so we add A to itself to double it. We're actually adding L here, although we technically don't need to. I suppose because these bottom 2 bytes are 00, you don't actually need this command. I've just kind of put it there because usually when you're adding an offset to a memory location, you do need to add L in, but in this case you could delete that, it'd still work fine. So then we've got HL pointing to the correct memory location of the color, and on the Amstrad CPC Plus, color 16 is the border, so we don't need to do anything special for the border. And so then we just write the 2 bytes that were in HL at this point but are now in DE, and that sets our color definition. We then swap DE and HL back, and we then turn off the plus registers, and that's really it. Very, very simple. Now, one thing I should point out is today's tutorial, we're actually recompiling the code to enable the CPC Plus features. So we've got 2 versions of our code. That's nice and simple for an example, but we can detect the CPC Plus by doing some tricks. We're going to have a look at that in a later lesson. So for now, we're just going to do this thing of having 2 compiled versions. And if you're making a very big game, that might actually be your best option anyway, because having 2 code paths will increase your memory size of your program. So having 2 separate programs might actually be better for you in the long run. So it just depends on how much memory you've got and how big your game is, whether you prefer to have 1 version or 2 versions. So that's the CPC Plus version. So what about the CPC? Well, we're going to skip over this bit for starters, because as you can see, it's for the V9990, which I can't test because I don't own one, and there's no emulator that supports it yet. So in theory, this would work for the V9990 on the Amstrad CPC, but we'll have to look at that another day when I've got hardware to test it. So how are we actually getting our information to the CPC? Well, the CPC, if you're working in BASIC, uses system colors from 0 to 26. So 0 would be black and 26 would be white. Now, we're not using these because those would mean us using the firmware to set the colors. We're using the actual hardware level color information. So we're sending data straight to the graphics system, and that means we're not using the firmware at all, which is the way I tend to prefer to do things in these tutorials. So this is our color 0 here, which is black, and then as we go across here, the blue gets brighter. As we go down here, the red gets brighter, and as we jump to the next table and the next table, the green gets brighter. So if there's an F in our green color here, we will be in this table. If there's an 8 in our green information, will be in this table, and if there's a 0, it will be in this table. Now anything in between will jump down. We're rounding down in this case, and that's why if you looked at my example before, you remember I had a grey colour that appeared on the CPC Plus, which was using 222. Well, on the CPC, 222 gets rounded down to 000. So that's something you need to be careful of, and if you were wanting it to round up in some way, you could modify the code, of course, to do this. But really what we're doing is we're converting those nibbles to lookup values for this table here, and the way we're doing that is pretty straightforward. So first we're loading in A, which is the colour number, into C. We're loading B into as 7F, and this is what we're going to need for later when we do our out commands. Next we load in L, which will contain red and blue. So first we strip off the top nibble here, and we run this CPC color conversion command here. And what this is doing is it's basically putting a threshold in where our colour will be either converted to a 0, a 1 or a 2. And that's because we've only got 3 levels of colour for each of our channels here. And so this one doesn't need bit shifting in any way. And so we're just running it straight away, comparing with these and then jumping to one of these colour conversions that loads A with a value from 0 to 2. And that now puts us in a position where we're ready to use that colour information. So at this point we then load that value into B and we get the value of the colour definition back, and we select the bottom nibble. We then use this alternate version here, which does some bit shifting first, but then does the same comparisons and returns another value in the same range. We then load that into L. We then do the same again for green. Now there is no information in the H component in the top nibble, so we just run this colour conversion command here again, and then we store the value in here. So now H, L and B will contain the red, green and blue information in a format of 0 to 2. Now all we need to do next is convert those into an offset for our colour information table here. So if you remember, we had 3 tables with green and each one contains 9. We had 3 lines for red and each one contains 3. And because of that, we have to multiply our H value by 9, which we're simply doing here by adding H 9 times. We need to multiply our red component by 3, so we're adding B 3 times because B contains our red component. And then we just add L because that's our blue component here. So this is now the correct offset in that table for the colour we want to show. All we do then is we add the start of the palette table here to the selected offset. We then read in A, because A is going to be the hardware colour that we want to send to the screen. We then do an out command after popping our BC, which will get the colour select for the gate array, which selects the colour, and for the colour number here. And so that will tell the system the colour we're going to change, and then the next command is the colour that should be changed to. And that's really all there is to it. So, I mean, honestly, this isn't the most efficient way you could do this. I'm sure there's better ways you could do it, but changing colours on a system is really not going to happen very often. You know, you're not going to be changing colours many times, and when I've used this code in the new Chibi Akamas minigame that's coming out soon, I am using this code, but I'm only using it when the colours, and I'm using it for the raster changes, so it's happening every frame, in every interrupt frame. But what I'm doing is I'm calling this when the level needs the colours to change, storing the result, and then writing that result to the raster interrupt code. So this is only being used once or twice a level, and the result of this is being used five times a frame during the raster interrupt. So as I say, this is not efficient code. It was kind of fairly quickly done just to get it working. It's not a time when you need to really start grinding the efficiency out. You want to focus your efficiency coding on things like your sprite routines, where loops are run hundreds and hundreds of times per frame. Something that you're running once when your game starts, that doesn't need to be efficient. It's not really worth the effort. In some ways, it's just better to just have code that is easy to read so that you don't get confused what it does or have trouble if there's bugs in it. So, as I say, I'm not claiming this is super efficient code. It certainly isn't. It just gets the job done. But what is important is it's converting that CPC Plus color definition into a conventional Amstrad CPC color definition. And you will see this color conversion routine used again in the future, because if we change the values in this table and the command that actually does the work here, we can easily convert this code to make it work on a totally different system that also has a fixed palette. So we can use this on the ZX Spectrum even, for example, just by converting these to the nearest spectrum color that for each of the palette definitions. And we could do it for the MSX1 as well. So, as I say, this is a nice, simple way of converting a RGB value into a fixed palette value. So it's probably worth you having a look at if you're looking to start working on another system that I don't cover in my tutorials. So we've looked at the Amstrad CPC today and the CPC Plus. We've got lots more systems coming in the future. I'm planning to have a look at the Enterprise, and maybe I'll manage to squeeze in the Sam Coupe next week as well. But we're going to do this on every single system we've covered that is capable of those RGB colour information. So we're going to have a look at the Game Boy and the Game Gear, and we're going to have a look at the MSX too, of course. So lots more coming up there. So I hope you've liked today's episode. Please subscribe to my channel and give the video a like if you have. As I say, we've got lots more coming on the CPC Plus as well. We are going to have a look in the future at how to detect hardware as well. In today's lesson, you were just uncommenting this option here to enable CPC Plus, or commenting it out to disable it. But in the future, we are going to have a look at hardware detection and how to detect if your system has a CPC Plus ASIC, which is the way you detect if a CPC Plus is present, and also how to detect how much memory a CPC has, as well as detecting ZX Spectrum 128Ks and various other things as well. So we are going to have a look at hardware detection in the future, but it's a bit tricky, so we're not going to look at it at this stage. So for now, we're just going to enable our advanced features just by remming out these kind of comments, and just by having different builds of the game for our CPC Plus and our regular CPC. Anyway, hope you've enjoyed today's lesson. Thanks for watching, and goodbye.